So yeah, my name is Alejandro. As many of you can guess, I'm Spanish. Sorry to make the joke, but no, it's not coming home. So yeah, moving on to important matters. Certus, so it's a collaborative project between Horiba Myra, Polestar, IPG, Connected Places Catapult, and Coventry University. I will introduce a bit what we have been doing. So we start with the problem. Obviously, everything you develop must address a problem. So we start with our V&V workflow. So this is a toolchain for the verification and validation of autonomous vehicles and autonomous features, ADAS, autonomous driving. So we start from the input. So the input, we need an ODD. We need to know what we are going to test. So this input can come from regulations, from requirements, from the customer ODD. We want to make sure that our system behaves safely, behaves well in these situations. What we then do is we define in the Pegasus layers the logical scenarios with their parameters. We agree with a customer if what parameters they want, what values, etc. Then we start with a closed loop. So first we sample the problem space. I will expand on this later on. And then we test. So we have an approach of a multi-pillar testing, which is simulation, physical testing, and mixed reality, which is a bit of a mix of both. Then we assess the performance of the system under test, we analyze the results, and then once you have all the data, you put that into a safety case, you need to argue. So we start from a simple example. This is an AEB scenario from Euro NCAP, and these are the list of parameters, like a best constraint scenario. So not all of these parameters are considered by NCAP. And we have more or less the amount of tests that is here. So NCAP only considers in scope about 20,000, out of which in the protocols there is only 300. So that means about 1.5% coverage. If you do a constraint-based effort, that number goes up to 50 million. Obviously, if you consider all possible scenarios, that goes out of the roof, is billions of scenarios. So what we're trying to achieve is how can we get to, let's say, the same result with less testing? So what tests are more important than others? How do we know that we have tested enough in this area? So these are some of the questions that the project Certus tries to answer. And we're focusing on three main questions: what to test, how to test it, and when to stop. So I think everyone can relate to these questions. They are the biggest issues in the industry for the verification and validation of autonomous feature. So what to test, I already explained a bit how to test it. As I said, physical, simulation, mixed reality, the multi-pillar testing capability. Obviously, then comes the problem of how many physical tests, how much simulation, how much mixed reality, and then when to stop. That for me is the biggest question of them all. So I will introduce a bit the modules. So we start from a customer feature, then we do the V&V specification, implementation, product acceptance, and release. So as I said, we start from an ODD, a list of logical scenarios that then we put into our tool. Our tool decides which concrete scenarios are going to be executed. Then we have developed metrics oracles in order to assess the performance of the system under test. And then we feed this information back to the decision maker of what next test we're going to run. And finally, we produce a report, a safety case, etc. So this is all a very complex project. Hopefully the next analogy will help you understand the whole concept. And hopefully you all have played Battleship. If you haven't, I cannot continue with the talk. But yeah, hopefully many people have played this game. So it's very similar. So you start with this 10 by 10. That's your problem space, and you don't know what's in it. So you need to sample, you need to throw shots, you need to put pins, and then your opponent tells you, yes, no, there is something here, there is not. So we start, let's say, with 10 pins. Where would you put them? You could put them, all of them, in just one little tiny area of the problem space. That's probably not a very good idea. You could scatter them. That's probably a much better idea. So it's very similar. We do the same. We start sampling the problem space. When we find something that is interesting, we focus on that area. We zoom in on that area to really assess what's there. And then once we have clarified what's in that area, we move to other areas. So problem space is 2D. In the battleships, it's 10 by 10. It's known. The stop criteria is very easy. Once you have found the 5 ships, you're done. Then feedback is very easy. Your opponent tells you it's a hit or it's a miss. And then the decision making, well, you use your brain if you have one. This is very similar, but very complicated for Certus. So in the battleship, the problem space is 2D. Here you know it. You know what your customer wants to verify and validate. You know the logical scenarios, but it's not constant. It's not always the same. It varies from feature to feature, from customer to customer. Then you have a stop criteria. In the battleship, it's very easy. Once you have found the 5 ships, you stop. Here, the stop criteria is when you stop. That's a very difficult question to answer. Now you have the feedback process. In the battleships, you say A5, and your opponent tells you yes, no. Here, you need to create a test, you need to execute them, and then you need to assess them. You need to put a mark. Was the driving safe? Yes, no. Was it correct? Was it what I'm looking for? Yes, no. And then you have the decision making. So in real life, it's very simple. If you have found something in A5, probably you're going to look at A6, A4, B5, because you know they can be structured like this or like this. If you put that into an algorithm that's called search space optimization, that's way more difficult. So hopefully the next graph will clarify this. So we start, let's say, with a problem space, and we sample 10 tests. So this is the meta model our tool creates. Basically, you cannot infer anything from it. It's very little testing. You go to 50 tests. You start getting an idea. It looks like in the right corner it starts going up, and the biggest problem is in the left bottom corner. Let's put more points. Oh, right now it's not just that continuity of the curve. There are like changes in gradient. So you get a clearer idea. And then once in 200 points, it's like, okay, this sounds reasonable. I think I can infer information from this meta model. Now, takeaways. So core innovations developed to test a self-driving features. So in this project, Polestar is one of the partners. We're testing on one of their features. So it's a real-world case. Then we have the intelligent scenario selection based on parameter sensitivity. So for example, I might decide that weather is a factor, and then you realize that, for example, for A, B, it doesn't make a difference whether it's cloudy or it's sunny. So we start reducing or eliminating the parameter weather, so that's parameter sensitivity. And there's a space optimization, so it's not putting all tests in one area or scattering them, is putting them on the areas that we think are more interesting or more efficient to test. And then it's an automated tool, so it's mostly based on simulation, but as I said, we can do physical testing, we can do mixed reality, but obviously simulation is way more efficient in terms of cost and timing. And then we have developed this novel mixed reality that we can do a mix of simulation and physical testing, so it is not as costly as physical testing, but still you have the accuracy of physical testing, the results.